Okay, this video is about the distribution of the sample proportion. Okay, so we're going to start off with an example. And this is about a homeowners association. Suppose there are 100 households in a homeowners association. A survey of all 100 households is done to determine what proportion favor a one-time assessment for roof repair. Okay, so you have a bunch of houses. Actually, maybe it wasn't roof repair. Maybe we'll change it to neighborhood improvements. Okay. The result is that 65 of 100 households approve the assessment. The proportion is P equals 65 over 100, which equals 0.65. So proportion is always between 0 and 1 inclusive. It could be 0, meaning no one is in favor. It could be 1, which is 100% in favor. And we can write it as a decimal, or we can write it as a percent. Okay, so then there's also the topic of, well, suppose you just do a survey of some of the members. Here's another example. There are 100,000 people living in a city. A survey of 60 people is taken randomly to determine what proportion are in favor of community. Oops. Hold on. How many M's in community? Oh, well. Community 4th of July fireworks. Show. A community fireworks show. Okay, so then they do a sample. And the result is that these are all made up problems, but anyway. Okay, the result is that 43 out of the 60 people surveyed favor a show, a fireworks show. This is a sample proportion. And we write p hat equals x over n. So p hat in this case will be 43 out of 60, and you can put that in your calculator if you feel like it. I mean, the other problem was a little bit nicer because I had out of 100, but this one, for whatever reason, I chose out of 60. So this is around, well, this is equal to 0.7166, keeps going on forever, so it's around 72%. Okay, now, does this mean that everybody in the, that it's exactly 72% of the people in the city? And the answer is no, because when you do a random sample, there's some chance involved of who you get. You might get one person as a favor and not another. I mean, if you would just pick one other different person, that would change. It might change from 43 to 44, or from 42 to 41. I mean, you know, just depending if you had just changing one person, okay? And that's just by randomness. But what we're saying is that we are going to estimate whether the true proportion is near this 72%. Okay, so what happens is, okay, so if we were to do the survey again, we would most likely get different results. So what we're getting at, because of chance, involved with randomly selecting participants for the survey, right? So that's why. So p hat is a random variable. And it turns out that the distribution is normal. So let's go through this. The mean of p hat is p. So what does that mean? That means if you kept doing the survey over and over for the city, you just kept doing them all the time, you just kept doing the survey over and over, each of those surveys would get a proportion. Those proportions, on average, will be the proportion of the whole city, which is, you know, we would think it's hopefully not too far away from 72%. That's a good question. By the way, over here, I should write X is the number of people who say yes. N is the sample size. So usually we use little n for the sample size, and often big N for the population size. Okay, so we have the mean is given right there. So that is mu p hat is equal to p. So if you averaged out all the p hats, you should, on average, you should get p. Okay, I mean not exactly, but it's the mean of that, the expected value of that. All right, and then the standard deviation of p hat is sigma p hat, and this is going to equal p 1 minus p all over n. And so what is the standard deviation? The standard deviation is a measurement of how close the p hats would be together. Okay, so again, here we just did one survey, and usually that's the case. But if you were to do a bunch of surveys, like 100 of them, and you plotted them, they would form a normal distribution. And a normal distribution has a standard deviation, which says how spread out the data should be. And here's a formula for this, where p is the proportion of the population. All right. This is really, like a hypothetical problem, because the problem with this formula, the thing about this formula is that the reason we're taking a survey is to try to estimate what the population proportion is. So we don't really know that. So what you can do is you can try to estimate by putting in p hat here. But we're not going to do that in this section, I don't think. So, okay. So there's formulas involved here. And here we see if we divide by n, and because it's under the radical, again, it's divided by the square root of n. So because it's under a radical, it's divided by the square root of n. So what that means is that the larger the population, the smaller the standard deviation is, and that would mean that the p hats you take are closer. They're more likely to be clustered around the true p hat. And so it's just saying that the larger n is, the closer your survey proportion is likely to be to the true proportion, which is something you would know without taking this class. You say, yeah, let's have more people, and we're going to get a better survey. But the thing is that actually you can apply numbers to this. So part of the thing that you do is that there are some things that we have that we sort of know anyway. Yeah, you ask more people, and you're going to get a better estimate of what the proportion is. But if you're actually trying to back up your findings with numbers and percents, we need statistics to do that. So that when you apply for a research grant or you're saying, look, we think this drug works or something, you need to offer numbers of percent likelihood that it's actually going to work. So let's look at this example here. So that's what, it's not just I think it is because I took a pretty large sample, but there's actually formulas and numbers that we can apply to that so that you can tell people, okay, this actually does work. Of course, the problem is that people try to essentially mislead and misguide people by tweaking those numbers. But that's, that's another story about how people can mislead by using, not unsound methods, which is an issue. Okay, according to the National Center for Health Statistics, 15% of all Americans have hearing problems. So it's better to have good hearing, especially when you get older, so you can stay in tune with the world, so you can stay connected to the world. Okay. Now in this problem, what we're going to do is we're going to say in a random sample of 120 Americans, what is the probability that at most 12% have hearing trouble? Okay, the thing is, that's a little bit tricky in itself. What do they mean by most? That is, what is the probability that p hat is 0.12 or less, given that the proportion of the America, the true proportion is 0.15. Okay, so when they say at most, that leads to this problem of less than, and that's always a little bit tricky. So at most means no more than 12%. So that could be 12%, 11%, 10%, or any fraction, a fractional number less than 12%. So what we're asking is, what's the likelihood that you go out and you take a survey and your survey gives a result less than 12% when it's a random survey? It's because 15% of all Americans have these hearing problems. So is it likely that we're going to have a problem here? I mean, that we're going to get 12%? So see, here's a normal distribution, and 12% is obviously less than 15%. And we're asking, what is the probability that we're going to get a p hat of 12% or less? I mean, you might get something more than 15%, something less than 15% when you do it, because it depends which people you ask. Even if you do a random, you might just happen to get a bunch of people with hearing losses. So what's the probability that you get less than 12%, which is asking this is, what is the area? Now, it's a little bit tricky here. We're going to use that mu p hat is equal to p, so that's all set up to go, which is 0.15, but we also have to find sigma p hat, and this one is going to give us a little bit of a trouble. Well, maybe not, somewhere along the way, maybe I'll write up here, n is equal to 120. So I'm going to find the square root of 0.15, 1 minus 0.15 over 120. All right, now the thing is, I really advise you that what you don't do is you don't do a bunch of rounding and then put the rounded number in the calculator. I mean, you might, here I'm doing a little bit of a calculation, but I don't want to round very much. And then what I'm going to do is this is a normal distribution, and I'm going to use the TI-83, and I'm going to do second distribution, the second one, which is normal CDF, and then for normal CDF, I'm going to just put in the left endpoint, which is, like negative infinity. So I'll put negative 10 to the 99. I'll put the right endpoint, which is 12, and then I'll put in mu p hat, which is 0.15, and then I will try to get this part here all without making a mistake. The more buttons I end up putting on the calculator, the more trouble I often have, which is, yet another reason to worry about a calculator. If you're at home, you don't have to use a TI-83 calculator. You could go online and do a search and look for normal cumulative distribution function calculators, and they have some online, which I think tend to work a little Well, anyway, I don't know which one works better because I haven't really. Yeah, I used one time, so maybe it's not that much better, but I think it should be. Okay, so I'm putting the numbers in, and let's see if I have a huge amount of trouble doing this. Once I put this calculator on here, I feel like that ends up being the thumbnail picture of the problem, and you're gonna wonder whether someone's getting money for that. Let's see if it does. Let's see if it ends up being the thumbnail of the video. So, okay, so I'm putting in the left end point, the right end point, the mean, then I have to figure out the square root. So I haven't really done that recently, but the square root's over here in yellow. So I'll do second square root, and then I'm gonna use as many parentheses as I can so I don't get this all wrong. I'll put parentheses 0.15 times 0.85, new parentheses. I don't think I should have to do that. I just overdo it on parentheses because I don't want to get something off here. Okay, that should close the square root. I'll put another parentheses to close the normal CDF. And nope. What happened there? Something went wrong with my parentheses. Oh, here, but E90. Okay, so I have to delete too much. I don't have that. Okay, so apparently that's proof there. I don't know proof of what, but that's what I wrote down. But anyway, okay, 0.178692832. So that's about 18%. So you have sort of a small chance. 18%, it's not that small, but a little bit small chance that you're going to get 12% or less. Okay, so that's what you got for that one. Okay, now all right, need more paper. Okay. All righty, so let's do part B. Suppose that a random sample of 120 Americans who regularly listen to music using headphones results in 26 having hearing loss, hearing trouble. What might you conclude? This is a made-up problem. All right, so this is a made-up problem. It's a really good question of what, what's happening listening to music on headphones, because it's so, common to listen to something on headphones now. All right, so we're starting off with, again, P is given to 0.15, so that's, that was given. And then we have X is equal to 26, N is equal to 120. So we're going to have the proportion of our sample. So see, there's the sample proportion, and this is the population proportion. So that's the, that's the amount of everybody around, I guess, America. And we're looking at the sample proportion, and that makes 26 out of 120. There's advantages of keeping things like that as a fraction, because this is 0.21666. If I'm going to have to use this number to punch in the TI-83 calculator, but it's probably better not to do that, not to round it off. I mean, what I'm saying is it's probably better to use this one, because you're putting rounding numbers into a into a formula, which, the calculator is grinding some numbers in a formula or something or other. And it's possible that actually that error will be magnified, will be amplified. Either way, I mean, you want to get the best, closest answer. So see what's going on then is that we have, but I like to get that number just to see what's going on. So because if we're saying that here's 15% is the usual level of hearing loss and all of a sudden it's 22%, then okay. So without taking a class or something, you're like, yeah, 22%, that seems a lot more than 15%. So it seems like those guys might simply, what's going on with that? Maybe they better stop listening to the headphones. But on the other hand, someone might say, well, you might have just by luck happened to have gotten people that have hearing loss, and it's just luck. So we're going to try to find this area so that we can determine whether, it's just a situation of luck that you happen to get people that have hearing loss. And so we're going to say, well, hold on. Well, let's just see what the probability is that just by luck we get hearing loss. And then we'll make a conclusion. And so I'm going to use the TI-83 again. Second distribution to normal CDF. And I have normal CDF, and I'm using 0.2 as my left endpoint. The right endpoint goes on infinity, so I'll write E99. And then I'll put in the proportion of the population, which is mu p hat. And then I'll have to put in, just a little bit of trouble, sigma p hat. So I feel like maybe I could have somewhere done this. I should have. Sigma p hat is going to be the square root of p, 1 minus p over n. So that's going to be the square root of, okay, good, I don't have to use this one, I can use this. 0.15, 1 minus 0.15 over our sample of 120. Okay, so I'm going to put that in there. And we'll see whether, let's see if we get a small number, or whether it's actually, it could happen. It could be that we just got some people that, some people who are just happen to be hard of hearing, okay, let's see what happens. So, okay, let me just punch those numbers. So it's second distribution, number 2 is normal CDF. So I put in, sort of covering things up. So 0.22 is the left end point. The right end point is infinity, so I'll just put a big number, e to 99. And then I will put in the proportion of the population, and then I'm going to try to do the square root properly. So I'm going to write 0.15, which is p, 1 minus 0.15, which is 1 minus p, divided by 120, which is the the sample size. All right, so what's the result? The result is a sort of small number. It's true this could happen. I'm getting 1.6% around. It's close to 2%. So there are less than 2% chance that there is a less than 2% chance that the higher proportion of people with hearing loss is due to the random selection process. Too many C's to process. Okay, it is more likely. Well, I mean, that's okay. How likely? it is likely that the high proportion is due to wearing headphones. Okay, so the thing is what we're saying is, why are we getting this high number? So we're getting 22% of those people have hearing loss, which is way more than the national average. Why is that? Is that because they're wearing headphones? Or is it because we just happen to pick some people that have hearing loss? And there's luck when I randomly select people. It's, you can use a random number generator. There's chance. I shouldn't say luck this side. There's random chance. So is it random chance? Yes. But the chances are small, less than 2%. And, there's a question of, well, okay, in what situation, how do you view 2%? Should I reject the idea that it was random chance? I think I should. Sometimes rejecting at 2% is not acceptable, I would say. For example, what if this has to do with a murder trial or some trial, and you're thinking, well, am I going to send the convicted defendant on this topic, on this, and send him away for prison for 20 years? If there's a 2% chance that the person's innocent, that it was just luck or a random chance that the data showed that, I don't think I should put someone away 20 years. But here, I would say, yeah, 2%, I think it's not just randomness. I mean, the stakes aren't that high. It's simply maybe people shouldn't wear headphones. However, let me just point out, this is a hypothetical problem. We made up problem. So I am not preaching anything, or I don't know what I'm preaching. I'm not advocating anything about headphones. For me, it's an open question, and also, maybe just don't play them loud. I don't know. It's not my field. Okay, so, alrighty. So, that's that.